in active inference, the world is described as a random dynamical system defined or described by a stochastic differential equation, like a Langevin equation. Why is that the starting point?
Should I explain briefly what a Langevin equation is, perhaps?
Sure.
So here's the thing. We want a fundamental theory of the brain and cognition, and we want it to be grounded in math and physics. Now, if you look at the fundamental theories that exist in physics, these would be general relativity, classical mechanics, statistical mechanics, quantum physics. They are all based on stochastic differential equations or Langevin equations. A stochastic differential equation is a very fundamental and also basic object. It's basic in the sense that when you're modeling a system, there are the known knowns and there are the known unknowns. Stochastic differential equation brings the two together. There may be the known knowns about the system, which could be forces that act on different components of the system. This is going to drive the system deterministically along a predetermined path. And then there are known unknowns. These could be random fluctuations. For example, if you have a drone, these could be random fluctuations due to wind. If you have a boat, random fluctuations due to waves. And these are things that you possibly cannot accurately capture. So you're going to summarize them in a random term. And then together, so you have this deterministic term that gives you a predetermined trajectory, and you have this random term that sort of perturbs the trajectory in a random way. And when you put the two together, you get kind of like a random evolution of your system with some structure. And this is basically what the Langevin equation or stochastic differential equation encodes. It's a very general starting point, and it's also the starting point that's consistent with the rest of physics. And that's why we start there when we think about the free energy principle.
Am I right to say that it's about the rate of change, some x, let's say, of some states? Is that so? That's kind of what we're looking at here. This notion of random noise. If you speak to certain philosophers, for example, they might say, well, it depends on who you ask, because for a universal, for some demon that knows the entire unfoldings of the world in a single glance, there's no randomness.
Sure.
And yet to us, the modelers, well, it's just computationally impossible to know every single element of the wind, let's say, or the waves. So what are we talking about? Are we talking about randomness in and of itself in the actual system that's being modeled, or for the modeler?
Here, it's agnostic in the sense that imagine you can model the system that you're trying to model in exquisite detail, so that you know absolutely everything that's going on. In that case, you would have no randomness. You still have a stochastic differential equation with no stochastic term, which is an ordinary differential equation, but it's still a stochastic differential equation, so the same math apply.
Sure.
You just have a random term that's like zero. Maybe there are things that you cannot model accurately in a system, so you put them in some noise, and the same math applies. So I would say it's noise from the perspective of the modeler or not, and we don't actually care. The point is that once you start from the assumption that you can model the system in that way, then things carry through. Most math and physics is based on Gaussian noise because it represents the world most accurately. You have something called the central limit theorem, that if you have a lot of like fluctuations, they kind of average away in a
like a pile of sand. Yeah.
So your noise turns out to be oftentimes very well approximated by a Gaussian process. But then there are instances where Gaussian noise is not accurate. So for example, if you're talking to people who model the financial market, they do not use Gaussian noise. They use noise with like jumps. So Gaussian noise is a good place to start. I think ultimately, as we work on the free energy principle mathematically, we want to be much more inclusive. So the Langevin equation gives you the rate of change as a function of the flow and a random component. Then when you sort of solve that, you sort of get, this is the probability that the system takes this trajectory, and this is the probability that gets this other trajectory, and so forth. This information is what's carried in the path integral formulation. The path integral formulation gives you the negative log probability of a path. And then you have the Fokker-Planck equation, which says at any point in time, this is the distribution that encodes the system in a predefined place that, the system might start in a particular location in state space. Then because of the flow and the random fluctuations, at time t+1, the system will be it could be here, it could be there, it could be there with a different probability. And then there's a probability distribution that summarizes this. And this is what's encoded in the Fokker-Planck equation.
Let's jump into the Fokker-Planck equation, because I've been doing some reading. So from what I've learned, it's a partial differential equation.
Yeah.
That relates the rate of change of the probability density function.
Mm-hmm.
So that's that P with the little dot and X, comma T, with respect to time, drift, and diffusion.
Yeah, it's a great summary.
If we were going to cast this in terms of just Cartesian coordinates, just X and Y axes, would it be right to say that we could have the X would be the position of some particle, and the Y would be the probability of finding it there?
So the Fokker-Planck equation would be that. So at each point in time, the solution to the Fokker-Planck equation is the density of the system that evolves over time. And so you could plot this on the XY axis, as you said. On the X-axis, you would have the position of the system. Cool. And the Y-axis, you would have the probability
distribution.
And so if we imagine things are simple, so if we imagine the system is always Gaussian distributed according to a Gaussian distribution, then if you solve the Fokker-Planck equation, you would have a Gaussian that evolves over time. So the mean would be shifting and the variance would be shifting also potentially.
So how would we then integrate time? Is it this like is that X and Y axis considered like a snapshot in time?
Yep.
Okay, excellent. So this gives us density dynamics, but when we talk about active inference, we talk about steady state densities. Right. So people, I think, have this intuitive notion from whether they're coming from dynamical systems theory or something else of a kind of basin, right? An attractor set. I mean, I think of it kind of like a magnet. How do we get from density dynamics to a steady state density?
So I should caveat this by saying that the latest formulations of the free energy principle are not based on having a steady state density. That's kind of like a new thing. And I think for like intuition, it's best to think about the steady state case. The intuition is that if you're modeling an agent, it has a preferred set of states that it likes to come back to. It does everything it can to be back at those states, like homeostatic states. You can also think about the fact that if you're modeling a system that does not dissipate in time, so let's say like not a gas, for instance, then the system should also have like a steady state. And the free energy principle is about modeling or analyzing those systems that have a steady state, that have these sort of preferred set of states. If a system has a preferred set of states and it's also decomposed into an organism, its boundary, and what's not the organism, then you basically look at what the internal states do, what does the boundary states do, how do they evolve, and what do the external states do. And then the conclusion is that in general, the internal states, you can describe them as inferring the external states.
I was curious more about in terms of the Fokker-Planck equation. We had this probability density function. We have our X, we have our position, Y, we have our probability distribution. Let's just say it's Gaussian. And per attractor state, per organism, per attractor state, it's going to be different, right? So mine might be really close to this side, yours might, whatever. What I kind of understood as a steady state is over time. So let's say now we like put all of those images of the X and Y axis on top of each other. If it's steady state, you expect that probability distribution to like stay on top of itself. If it's not, you'll expect it to shift from side to side.
Yeah, or like become completely flat.
Or become completely flat. I guess reincarnation would be kind of Gaussian, flat Gaussian. It was a tongue-in-cheek comment, but I have a Gaussian distribution of being in a certain state.
Right.
I die, I enter into the ether, I dissolve into the heat bath, I flatten out, and then I reappear as a frog and I enter into a new Gaussian distribution.
Yeah, that's a good way to put it. I think there's kind of like two scenarios. One is that there's no steady state and the system dissipates, and therefore your snapshots of the density at each point in time will converge to a flat distribution. And the other case is that there is a steady state and the snapshots converge onto like a clear, well-defined distribution. The point of a steady state is that if you start the system in that distribution, it will remain in that distribution.
And that's strict? You will stay within that distribution? Or is there permission, let's say, in sentient creatures like our own for that distribution to change somewhat?
There's kind of like two answers to that. You being at a pre-specified distribution does not mean that you're not doing interesting things. So if we just think about a convection cell or a tornado,
Right.
you have like this circling around. The probability distribution of where the gas is or where the tornado is just stays constant. It's kind of like this. But you still have some interesting motion inside.
Over time, it will look like I'm converging on that state, but I might not always be there.
It's kind of like hard to wrap your head around.
Yeah. Think about like homeostasis, right? If you model temperature, you can imagine it will have a Gaussian distribution sort of with the peak at 37.9 degrees centigrade, let's say. But you are not going to spend your entire life at 37.9 degrees centigrade.
Exactly. You're going to move around, and on average will be according to this Gaussian distribution.
Okay, good. I want to jump to that notion of the internal states tracking the external states. So the way that I read internal and external is tracking and tracked, because the internal-external is such a philosophically troublesome distinction. And then I think of something like the equation for variational free energy, and I think about the KL divergence between the recognition density and the true posterior, and the maximization of model evidence. I don't have to necessarily make this strict distinction between the internal states, my states, and the worldly states. Because all I'm doing here is I'm saying I have, given some observation, I have a probability distribution of some state. For me, I think you could pose that actually all that we are just this aggregation of worldly states. And then you have the maximization of the model evidence, which is the probability of Y given your model. There's nothing like internal that's going on there. It's just statistics. Do you think that it's somewhat troublesome to put this little homunculus or this little ego in the internal states and being like, he's doing sufficient statistics? Do you see that as slightly troublesome?
Internal and external states can be interchanged. It's all about the blanket. The external states could be part of your own body, and the internal states could be part of your brain, and the blanket somewhere in between. Or the internal states could be like a school of fish, and the external states could be like a predator.
I always thought that things that seem to persist look like they're maximizing model evidence for themselves.
Two things we're touching on here, because tracking and the model evidence, they're kind of like two things that are going on. Because when you think about it, the free energy is this KL divergence plus the surprise. And we use this tracking to minimize the free energy.
Well, the way I'm trying to frame it is that entails some form of tracking. You've got that probability of Y, but it's sort of given your model.
There's another important point that came out in the research. A lot of people say that you can always interchange internal and external states, and that one is tracking and the other is tracked. But it turns out that this is not always the case, because for the internal states to track the external states, they need to have enough representational capacity to make inferences about all the internal states that are out there. They don't have enough representational capacity. Maybe they might just infer some or infer linear combinations of external states. In any case, they're just going to have part of the picture.
No, that's interesting.
Which means that for external states to track internal states, they also need to have enough representational capacity and a sufficiently high quality coupling with their own sensory states with the boundary to make inferences about the internal states. So you always have this synchronization and this inference going on, but you cannot necessarily say that the internal states will be tracking all the internal states all the time, or vice versa. It depends on the nitty-gritty of the coupling and how much representational capacity these states have.
Well, again, that's why for me this maximization of model evidence just seems a little bit simpler, because whether you're a drop of oil or a rock or a human, we can sort of, not arbitrarily, but we can generously give out models for each one of them and say that they look like they're maximizing model evidence. How long something lasts is a different question. The salt that I put in water maximizes model evidence for itself being salt for a very short amount of time. You could cast that as its surprisal being very high, but at least for while it's salt, it's maximizing model evidence. And then I guess it's maximizing model evidence within a Markov blanket that's the water salt solution.